right, let's talk about phase diagrams. And what phase diagrams do is they describe the relationship between pressure and temperature with respect to the different states of matter. So over here, let's just get the features. On the y-axis, we have pressure. On the x-axis, we have temperature. And then in this area of the phase diagram, we have solid. Over here on the right, gas. And in the middle, the liquid phase. These lines, which describe conditions of pressure and temperature at particular combinations, are called phase boundaries. And phase boundaries are areas of pressure and temperature in which the phases are in equilibrium with each other. So anywhere along a particular phase boundary, the states of matter are in equilibrium. That is, the phases coexist. Okay, so this is the phase boundary between solid and liquid. And so let's pick a particular combination of pressure and temperature. And at that particular combination of pressure and temperature along that phase boundary, you're going to have solid and liquid in equilibrium with each other. They simply coexist together. A couple of other features. Well, on this phase boundary, you would have liquid and gas in equilibrium with each other anywhere along this phase boundary. So if I picked a particular point, which is a combination of pressure and temperature, ignore my not so straight lines, this would represent vaporization or boiling, a temperature-pressure combination that would exist where boiling occurs. And anywhere at that temperature and pressure combination, you have an equilibrium. And phase changes are equilibrium situations. This would be the phase boundary between solid and gas. This is from going from solid to gas directly is sublimation. So whatever this particular substance is, at this particular combination of pressure and temperature, you would have the equilibrium between a solid going to a gas and a gas depositing into a solid. Solid to gas is sublimation, gas to solid we call deposition. Let's talk about this point right here. I'm betting by now you can figure out what is occurring at what we call the triple point. At the triple point, you have all three phases in equilibrium. Okay, so all three phases are in equilibrium at this particular combination of pressure and temperature. Okay, there's another point I want you to be aware of. This is called the critical point. And the critical point is a combination of temperature and pressure where the distinction between liquid and gas phases disappears, and you can no longer condense a gas to a liquid beyond the critical point. And so what we have here in this area are what we call supercritical fluids. And supercritical fluids can have some interesting uses. Okay, so supercritical fluids, you can no longer compress a gas into a liquid, and the distinction between gas and liquids disappears up here. It is speculated or calculated that if you go to the gas giants like Jupiter and Saturn, which are principally gas, and you go down to some depth in the gas giants, you'll find areas of supercritical fluid because the pressures are so high due to gravity, the temperatures are so high that You have gases that are no longer gases, they are supercritical fluids. Now we can use supercritical fluids. I believe they use supercritical carbon dioxide, somewhere beyond the critical point, for the decaffeination process. So you can decaffeinate coffee and different beverages that contain caffeine using supercritical carbon dioxide, because you can actually dissolve substances, solutes, into supercritical fluids, and then all you have to do is release the pressure, and what happens is you get this instant evaporation at high temperature of all of your solvent, and what you're left with is your chemical. You have supercritical water reactors, nuclear reactors, that operate at pressures around 21.8, almost 22 atmospheres of pressure, and temperatures around 374 degrees Celsius, which is about 674 Kelvin. So that's water under extraordinarily high pressure and temperature. Let's take a look at a comparison of CO2 and water phase diagrams. They have the same general features, solid in green. Here the blue is the liquid in both cases, and then the tan color represents the gas phase. And they have the same features. You have the critical point, you have the triple point in both diagrams. But on the carbon dioxide phase diagram, you'll notice that the triple point exists at 5.11 atmospheres thereabouts. So what that means is that at normal atmospheric pressure that you and I are experiencing right now, there is no liquid phase for carbon dioxide. So down here at 1 atmosphere, you only have the solid and the gas phases for carbon dioxide. The solid phase is called dry ice. We use it to keep things cold. It lasts a long time, but it doesn't have a liquid phase. It sublimates directly to the gas phase, which CO2. If you put carbon dioxide in a closed container and warm it up, allow it to simply vaporize, to sublimate to the gas phase, eventually you'll build up 5.11 atmospheres of pressure, and you will begin to get a liquid phase for the carbon dioxide. Supercritical carbon dioxide. Remember that supercritical fluids, like supercritical carbon dioxide, you can't distinguish between the liquid and the gaseous phases, so you can actually dissolve solutes into that supercritical fluid and then simply release the pressure after your chemical reaction is over, and it will vaporize pretty much instantaneously and just leave you with your chemical reaction left over. Over here, looking at the phase diagram for water, we see the same principal features: solid, ice, liquid water, and then gaseous water. And our triple point is down here well below 1 atmosphere of pressure. So we have all 3 phases at 1 atmosphere of pressure. But I want to draw your attention to this. Let's say you have 0 degrees Celsius, maybe even a little less than that. So you've got, let's say, ice that's at a temperature of, let's say, -5 Celsius. And we raise the pressure without raising the temperature. Eventually, when the pressure becomes high enough, and that is somewhat over 1 atmosphere of pressure, the ice will melt into liquid water simply from the application of pressure. So you'll have liquid water at a temperature that is colder than 0 degrees Celsius. However, the pressure is higher than 1 atmosphere. So it's always been explained to me that the way ice skating works is that pressure is defined as force per unit area. So you take the mass of a human being, And instead of having them stand on their feet, they're standing on this thin little ice skating blade. So now you have more force per unit of area, and because of that, what's happening is underneath the blade is you're melting the ice, and that's providing a little sheen of water along the ice, which makes the ice skate slide along on that very, very slick surface. That seems like a reasonable thing to think. I have not experimented with that. I can't testify to it personally, but it seems like a reasonable thing to think.